This is topic 10.11, Taylor polynomial approximations. We're just going to jump right in and let's talk about why we use Taylor polynomials. Taylor polynomials are created to help us approximate other functions. Now, why would we do that? Why would we come up with a polynomial to approximate some other function? Well, we already know that polynomials are very easy to work with, especially in calculus. We can take the derivatives or integrate without an issue. This allows us to evaluate difficult functions with a very simple function. Now, a Maclaurin polynomial is a special type of Taylor polynomial. A Maclaurin polynomial has a center at 0. So that will be nice. So basically what we're going to be doing is we're going to choose an x value to center our polynomial. And you can go ahead and just call that C. So C is the center. Okay? The approximation is going to have the same y value as the original function. So if we move this C equals center, we want to say that f of C is equal to the polynomial that we will use evaluated at C. So at the center, these are the same. Okay, so this is your original function, and this is your polynomial. Okay, so we will expand the approximation about x equal to c. So another way to say this is the functions are centered at x equal to c. Okay, so let's just go ahead and try a basic example and build on that. So we will begin with f of x equals e to the x, and we are going to have the center at 0. So what do we know? We know that f of 0 is equal to 1 just by looking and evaluating this function. Okay? What do we need? We need the polynomial evaluated at 0 to be equal to 1. So we want to make the graphs have a similar shape at the point where x equals to c. They should have the same slope at that value. And that leads us to the derivative at c needs to be equal to the polynomial's derivative at c. Again, this is the derivative of our original function, and that p prime of c is the derivative of our polynomial function we will be using to approximate. So what does this mean? That means that f prime of 0 is equal to p prime of 0. And so if we go ahead and use the point slope form of a line, and we have y minus the y value equals the slope x minus the x value, and we go ahead now and fill that in, y will be our polynomial evaluated at x minus f of c, our function evaluated at the center, equals f prime of c times x minus c. I think this right there needs to be x1. Okay? And so that's the point slope form. Maybe I better write that out. Okay? And so now, if we want to go ahead and just solve for that polynomial, we would add f of c to both sides. And now this is starting to look like something we're familiar with. So since we have c equal to 0, we can now say that p of x is equal to f of 0 plus f prime of 0 times x minus 0. And that simplifies to p of x equals, and f of 0, let's go ahead and find those values. So since we have f of x equal to e to the x, we know that f of 0 is e to the 0, which is 1. We also know that f prime of x is equal to e to the x, and f prime of 0 is also equal to 1. Okay? So now we will put those values in. And we have f of 0 is 1 plus 1 times x. And that leads us to p of x equals 1 plus x. And that is the polynomial we will use to approximate f of x. Now, and this is what I'm going to put here since c was equal to 0. Okay, and this is actually called a first order approximation. A first order approximation. And it works for a small interval around our point of center. Okay? So let's make a note here. P of x approximates f of x when x is close to 0 in this problem. Okay? And I'll put a little star there. Now, what if we wanted a higher order to improve the approximation? Then we could go ahead and get our higher derivatives and go to the second derivative evaluated at 0, and we'd come up with a second order approximation. P of x equals 1 plus x plus 1/2 x squared. And we could keep going. And if we are centered at x equal to 0, we could end up with the following pattern. And you can see that right here. So the nth order approximation, that's what this is, the nth order approximation centered at 0 is equal to p sub n of x, as shown. Well, that's a lot of work creating those. So what we came up with is what we call an nth Taylor polynomial. And this is how we will write an approximation of f centered about x equal to c. So this polynomial will approximate f when x is equal to c. And it looks like this. F of 0, and that's always going to be your very first term, plus f prime of 0 times x. Whoops, let me start over. I was working on the Maclaurin. F of c, so that's your function evaluated at c, plus f prime of c times x minus c, plus, and now we have the second derivative evaluated at c times x minus c squared over 2 factorial. And yes, you could have written 1, first derivative is shown, over 1 factorial, and you could have written x minus c to the 0 power over 0 factorial. You could have done that, but it is not typical to write those values that all equal 1. I will mention that both 0 factorial and 1 factorial both equal 1. So that's important to note. Plus, let's go ahead and write the third derivative evaluated at c times x minus c cubed over, you guessed it, 3 factorial. Plus dot, 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 and now we will write our nth derivative evaluated at c. Let's see if I can make this just a touch smaller, not much. There we go. Times x minus c to the nth power, all divided by n factorial. And n is the order of the approximation. Okay? So we can approximate any function using this nth Taylor polynomial. Okay, what's the good news? The Maclaurin polynomial is just a Taylor polynomial centered at x equal to 0. So we are very happy that we're not having to learn a new formula. And it looks just like that. And it is f of 0 plus f prime of 0 times x, since c is going to be 0, plus the second derivative evaluated at 0 times x squared over 2 factorial, plus the third derivative evaluated at 0 times x cubed over 3 factorial, and finally the nth term, 0, x to the nth divided by n factorial. So n here is again the order of our approximation. I think we should jump right in and get started. Let's look at number 1. Find the third degree Maclaurin polynomial for f of x equals e to the 2x. So if we want the third degree polynomial, we know n is going to equal, we will need n is equal to 3. Let's just leave it at that, okay? And if it's Maclaurin, we know that c is equal to 0. So let's first write out what we need. The third degree polynomial of x is equal to f of 0, evaluated at 0, plus f prime of 0 times x plus f double prime of 0 multiplied by x squared divided by 2 factorial plus the third derivative evaluated at 0 times x cubed divided by 3 factorial. So what do you see? Yes, we need 3 derivatives. So let's go ahead and write f of x equals e to the 2x. F prime of x equals 2e to the 2x. F double prime of x is 4e to the 2x. And f triple prime of x equals 8e to the 2x. Now evaluating each one of these at 0, you will see that f of 0 equals 1, f prime of 0 equals 2, f double of 0 equals 4, and f triple of 0 equals 8. Okay, so now we can go back over to our third degree polynomial, and f of 0 we have as 1 plus f prime of 0 is 2 times x plus f double prime of 0 is 4 times x squared over 2 factorial. I'm going to write that as 2 times 1 plus 8x cubed divided by 3 times 2 times 1. Now we can go ahead and simplify, and we end up with 1 plus 2x plus 2x squared plus 4/3 x cubed. And what is this? What is this that we just found? What it is, let's make this square a little bit like that and move it up just a touch. What we found is the approximation. Let's write it right there. This function approximates f of x when x is close to 0. And you'll see here in our example below that the values they ask us to use for the approximation, they are close to 0. As you can see, 0.2 and 0.2. So let's take a look at this. What we want to say is that f of 0.2 is approximately equal to the third degree Taylor polynomial evaluated at 2. And that's equal to 1 plus 2 times 2, plugging in 0.2 here. 2 times 0.2 plus 2 times 0.2 squared plus 4/3 times 0.2 cubed. And I came up with 1.4907. And what's really interesting is that f of 0.2, if you would put that in the calculator, f of 0.2 is equal to, remember f of x is e to the 2x, equals equals e to the 2 times 0.2. And if you put that in your calculator, you'll get 1.4918. This looks funny. Let me just fix that up. and that's about equal to 1.4918. So look at this approximation that we have from our polynomial and look at the actual value. They are very close. Okay, let's try another example. Find a fourth degree Taylor polynomial for f of x equals the natural log of x this time, centered at x equal to 1. So this is not a Maclaurin. As you could see here, that was a Maclaurin. We do not have the center at 0. It's at x equal to 1. So we will find a fourth degree Taylor polynomial for f of x equals the natural log of x. I like to write these out first so that I see what I need. So the fourth degree Taylor polynomial is always the function value evaluated at the center. So that's f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 times x minus 1 squared over 2 factorial plus f triple prime of 1 times x minus 1 cubed over 3 factorial plus the fourth derivative evaluated at 1 times x minus 1 to the fourth power divided by 4 factorial. So as you can see, we are going to need the first through fourth derivative, okay? So we'll go ahead and write those over here. So we have f of x equals the natural log of x, and see if I can move that. F of 1 is 0. F prime of x equals 1 over x, and f prime of 1 is 1. F double prime of x equals negative 1 over x squared, and f double prime of 1 is negative 1. We have two more to go. F triple prime of x equals a positive 2 over x cubed, and f triple prime of 1 is 2. And one more, see if I can move these up just a touch. And the fourth derivative evaluated at x is a negative 6 over x to the fourth. And that derivative evaluated at 1 is negative 6. And so now we can plug these values in. So we'll go back over here and say the fourth degree polynomial is equal to f of 1, which is 0. F prime of 1 is 1 times x minus 1. And then f double is a negative 1 times x minus 1 squared over 2 times 1 plus 2 times x minus 1 cubed over 3 factorial. And then we have minus 6 x minus 1 to the fourth power over 4 factorial. And you can see here that this works out to be x minus 1 minus 1/2 times x minus 1 squared plus 1/3 x minus 1 cubed minus 1/4 x minus 1 to the 4th. And this is our 4th degree Taylor polynomial. Now, let's see if we can use this polynomial to evaluate f of 1.1 to approximate it. Okay. So, let's do what we did before. We'll go ahead and write that f of 1.1 is approximately equal to the 4th degree Taylor polynomial evaluated at 1.1, which is equal to, and now we're going to go ahead and plug 1.1 in here for each x, and that would be 1.1 minus 1 minus 1/2 times 1.1 minus 1 squared plus 1/3 times 1.1 minus 1 cubed minus 1/4 times 1.1 minus 1 to the 4th power. And this is just 0.1 minus 1/2 times 0.1 squared plus 1/3 times 0.1 cubed minus 1/4 times 0.1 to the 4th. And I went ahead and worked this out, and I got 0.0953083. And move that up just a bit. Let's see what f of 1.1 really is. So if you want to, make a note that f of 1.1 equals the natural log of 1.1, and that's about equal to 0.0953101. So look how close these two values are. Again, this is our approximation from the polynomial. And this is the original function value. Okay. So, I also want to make a note here because sometimes students appreciate this. P4 of x approximates f of x when x is close to 1. So I think it's really nice to have that statement written. Okay, I wanted to point something out. Take a look up here in the Taylor polynomial, and do you see that all of this is the coefficient of this x term, and this is the coefficient, and this is the coefficient of the nth degree term. So that is really important to note, and we will go ahead and define that right now. So the coefficient of so this is our coefficient of the nth degree term in a Taylor polynomial centered at x equal to c is the nth derivative evaluated at c divided by n factorial. So let's try an example that uses the coefficient. Let f be a function with a third derivative, so they actually gave us the third derivative. What is the coefficient of x minus 2 to the fourth power? That means the center is at 2 in the fourth degree Taylor polynomial for f about x equal to 2. Okay, well, as you can see, we are going to need the fourth derivative evaluated at 2 divided by 4 factorial. So we need to go over here and find the fourth derivative, and that is equal to 3/2 times 8x plus 2 to the 1/2 power times 8. And that's equal to 12 times 8x, and we'll just write that as a square root. 12 times the square root of 8x plus 2. So the fourth derivative evaluated at 2 is 12 root 18. And of course, that's 36 root 2. So now we come in and put 36 root 2 divided by 4 times 3 times 2. And we come up with 3 root 2 over 2. And that will be the coefficient of the x minus 2 to the fourth power term. And that concludes this topic.